Howdy hi, Calculus AB intrepid explorers. We are on to day 69, left and right Riemann sums. It's kind of an imposing title. We don't know what a Riemann sum is at this point, so hopefully we'll learn what that word is, or if it's named after someone, or if it's just a word that's been in the English language this whole time you just never heard. To warm up today, we're going to remember our idea or our definition, our informal definition of definite integrals. Oof, easy for me to say. So what you are asked to do is identify the value of the integral from, need more space than that, of -4 to 12 of f of x dx. Now, last class, I'm sure you'll recall, you had to draw many graphs. Luckily, this class, the graph is drawn for you. So your goal is to find the value of this using our equation over here. Let's see what you can do, and then once you're done, you can unpause and see how you did. Ready, set, go. All right, we're back. I will tell you right now that some of you probably struggled with the fact that the answer is not 32 pi, but I'll show you how you got 32 pi because you do need that later on. You got 32 pi by recognizing that this is a semicircle. That's a pretty good line too, I'm proud of myself. And you said, I want to find the area of this semicircle. Well, that is very wonderful of you. So I'll do that because that seems like the cool thing to do these days. We are going from -4 to 12. So to find the distance between two things, you just subtract them. 12 minus -4 is a diameter of 16. And if I would like the area of a semicircle, the area of a semicircle is half the area of a full circle. Okay, so working further on, we have to do 1/2 pi area of a circle. Let's see, we need the radius, that's half of 16, that's 8. 8 squared, 64, half of 64, 32 pi. Ha! Now wait, we said that's not the right answer. And in order to know why, we need to correctly interpret what this integral is asking us to find. It's asking us to find the area between the curve and the x-axis. So if we draw maybe some dashed lines here, where is the area between the curve and the x-axis? Oh yeah, the area between the curve and the x-axis is, and I'm waiting for my pen to catch up with me, there we go, and I'll try to draw this sideways. Isn't that this area right here? That's a weird shape. And in fact, it'd be very difficult to find the area of the shape with one formula there until we realize that shape is actually made up of two formulas. That shape is made up of one large rectangle, like so, with this semicircle chewed out of the rectangle, right? Instead of drawing the rectangle like that, instead you could chew out or take out the semicircle and you'd go there. So I think what we should probably do is, if we want to find the green area, we are going to find the area of the full rectangle first. I'm going to go ahead and draw this like so. We're going to find the area of the rectangle, and then we are going to subtract the area of the semicircle. We'll pretend that's a semicircle. Sure. Okay. Well, the area of the rectangle, okay, area of the rectangle is 16 wide, and then how tall? Well, we can see that that's 10 right there. Okay, so it's 16 by 10. And then we have to subtract out the area of the semicircle, that's 32 pi, and we're looking pretty good so far. So what does this look like to me? Well, this answer I think is going to be 160 minus 32 pi. Except for one thing. If you estimate this, 160, let's call pi 3 for now. Engineers rejoice and mathematicians cringe. We multiply 32 by 3 and get to 96. I think if we subtract those, we'll get a positive answer. We could say that that's greater than 0. And I don't think we want a positive answer here. Where is that green area located? Oh, that green area is below the x-axis. And any time we have an answer that's below the x-axis, our answer better be negative. So how do we do that? Well, it's easy enough. We just say this is the right answer. We just need to make it negative. It's just going to be the opposite of it. And to be correct, we should probably go back through and put a negative on the end of everything. So it's basically saying once you do the math, make it negative. If you distribute this, it might give you an even better indication. Start with negative 160. Start with the entire rectangle, which is very negative, and then add back on, I keep trying to do 3 pi, add back on 32 pi, and once you've done that, you'll just have the negative green area remaining. Definitely a tricky question. It showed up about 4 years ago on the AP exam, so it's certainly worth discussing, making sure you're comfortable with that. But this is, for today, I think, the last problem we're going to see where the area is exactly calculable. Is that a word? Sure. Exactly able to be calculated using our area formulas. So let's go ahead and take a sneak peek at our main lesson for today. Similar idea. I have given you the graph of y equals x squared. It's this wonderful parabola, and your goal is to find the approximate area that is shaded in over here. Another way to think about it is you want to find the area from 0 to 2, right? Spanning that space between the graph of x squared and the x-axis. So we want to find this shaded area. Now there are many ways to do this, and I'm going to see who can be the most accurate when we actually do this in person. But since you're on your own, see if you can think of 2 or 3 different ways and at least implement one of them to try to approximate the area. And you are welcome to use your calculator if you would like. Ready, set, go. Okay. We're back, and let's see how you did. Now, I would say that the majority of my students go through and they say, well, couldn't we just make this a triangle? Look at that pretty triangle, and just approximate it that way. So maybe we'll call this the triangle method. And to find the area of a triangle, it's 1/2 times the base times the height. We should say it's approximated. The base is, of course, a length of 2, and the height looks to be a height of 4. So we get 8 divided by 2, which is 4. Say, cool, has an area of 4. All right, maybe pretty good. But then the question comes up, can we do better? And I think we could, right? What if we did something like this? What if we did, and I'll change colors, what if we did a nice little triangle like that, right? And then we did like a trapezoid over here, or if you want, you can think of it as a square with another triangle on top. That one looks better to me than the actual triangle, right? The triangle is certainly an over approximation. It has all this extra space in there, but the way that I sorted it only has a little bit of extra space. It just has these guys in here. Okay, that could be one way. Another way you could do it is, what if you just did it using squares, and you said, or rather rectangles, you just said one's here and one's over here. Is that better than the triangle? Is it worse? Well, let's look at the triangle that we just did like so. I bet that's probably going to be worse. It looks like it has more area, but it does work. Okay. Now, what we're going to focus on today is using rectangles to find area. Eventually, we will get back to this friendly triangle method, and sometimes the triangle is more accurate. Not always, but sometimes. Today, though, we're going to focus on just using rectangles, and I like to start with rectangles because A, they tend to be the most common, but B, their area formula is a little nicer because you don't need to include the 1/2. So just, even if you think it's not the most accurate, you're right. For many cases, it still is easy to work with, and I think it's going to make the overall concept easier to understand. Now, there are many different ways we could use this rectangular method. We could just draw one big rectangle and say, ha, I think the area is approximately, what's that, 2 times 4? I think the area is approximately 8. Well, good on you. I'm pretty sure it's less than 8. So then someone says, well, you used one rectangle that used the whole base. What if we just use a portion of the base and use that to make 2 rectangles? Is that closer? Well, this has an area of 1. This is 1 for a base times 4. That has an area of 5. And I think that is probably a little bit closer than the 8, right? The 8 included this whole portion, which is definitely extra stuff. Okay, but we could be even more accurate, right? What if instead of using 2 rectangles, I used, let's say, 4? And let's see, let's subdivide this interval down here. And what if I did something like this? Okay, wait, that's not what I wanted to do. That was awkward. What if I made a nice little rectangle here, another one here, and here, and here. Now we have 4 rectangles. Each one has a base of 0.5, or I'm going to write that as 1/2, and you can find the heights just by looking over here. And that actually looks even more accurate than when I did the 2 subintervals, right? Those 2 subintervals had one here and a second one up here. Yeah, they have all that extra space that we don't want, so I think I've gotten more accurate. This process of using more rectangles to get a more accurate approximation of the area is what we're going to focus on for today. So, depending on how you found the area, you may have divided your graph into a number of subintervals. Using the specified number of subintervals, find the area of the graph. So now we're going to look at 2 subintervals, 3 and 4. So again, I showed you how you could subdivide with 2 subintervals, and I also showed you 4. I didn't show you 3. It's a bit more of a challenge, but it's very much doable. But what I'd like you to do, please, right now is try to set up 2 rectangles, 3 rectangles, and 4 rectangles on this same graph and see what those approximations are. Okay? Once you're done, you can unpause and we'll chat. Ready, set, go. All right, now you're back. I'm actually not going to go over the answers for those. I have faith that you can determine them and they're kind of a means to an end. But I did want to bring up one thing. Looking at these 4 subintervals, I think we'll all agree that if I subdivide like this, we can see our 4 subintervals, right? We have, and maybe I'll do it in blue, first subinterval, second subinterval, third, and fourth. But depending on how you viewed this, you might have drawn your rectangles differently. For example, one of you might have said, well, I'm going to draw my rectangles like so. And you went over and did something like this, like I did. And that's totally fine. But then someone else might have said, no, 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 I don't want to do that. Instead, I want to draw my rectangles like this. And then this guy just kind of gets drawn straight across because I'm just using this left point over here for the height of the rectangle. And someone says, whoa, why would you want to do that? Right? Now you just have 3 rectangles. Clearly, that does not fill the entire area. Of course, your comeback is, but yeah, but if you, I said change colors, your comeback is, well, yeah, but the way you did it, like so, is too much area. Right? Clearly, you have all this extra space up here. And depending on what field of business you're in, is it better to underspend or overspend? And I think it probably depends on which side. If you're the customer, you'd say, please overspend on me and give me more. Versus if you're the person in charge of spending the money, you're like, I don't want to, I'd rather underspend. And then worst case, we can make up those little gaps later on. So there are a couple ways that we could have drawn these rectangles. There are actually more ways too. But those are the 2 ways that we're going to discuss right now. Before we do that discussion, we need a little bit of notation here and a little bit of history, and then we'll get back to those rectangles. But that's really all today is, just using different sized rectangles to approximate the area under the graph. And as a reminder, the reason we're doing this is because the area underneath x squared, and I should erase this again, the area underneath x squared is not a nice shape. I don't know how to apply a simple geometry formula to find this area. It's not a perfect triangle. It's a curved triangle, and I don't even know, it's not evenly curved. So how do we find that? And the answer is we don't at this point. So that's kind of a bummer. We're just going to be doing approximations, but eventually our investigation of approximations will lead us to how we can find the exact area, because there is a way to do it. It's calculus. Alrighty, some terminology. I have a very pretty graph here that is drawn in black that I am over highlighting in purple. This has been split into 7 subintervals, and we can see each subinterval. I'll do them in blue again, right? So we have the first subinterval, the second one, the third one, and so on and so forth. What we need to understand, though, is that each subinterval is bordered on 2 sides. For example, this first subinterval down here is bordered by this point, and on the other side, that point. We're going to give those points names in terms of x coordinates. Now, it is common, and computer science folks will like this, it is common to use our first point and call it x sub 0, the 0th point. Sometimes we would call that a. And then, of course, we have x sub 1, which is our second point, and so on and so forth, all the way up to x sub 7 over here, which is interesting because although there are 7 subintervals, there are actually 8 points, aren't there? 1, 2, 3, 4, 5, 6, 7, 8 points. The distance between any two x values, or another way to think about it is the base of any of these rectangles is known, and I'm going to highlight this up here, as delta x. So this distance right here is delta x. Of course, delta x is found by subtracting two x coordinates. So in this case, it'd be x sub 5 minus x sub 4 to find that exact base length. Okay. We also should realize that subintervals are not always even. Okay? Now, if they are completely even, and we can call all of these delta x, then you'll see the difference between two x values just given as delta x. If they are not even, then there'll probably be little subscripts here, like delta, maybe they could even put it after this, something like that, showing you that they're slightly different. In this case, though, we're going to assume that they are even, at least for today, just to make your life a little bit easier. Okay. Now, the first question we need to answer before we get better at approximating is, how can we find the length of delta x? And you're like, well, that's easy. You just take two x coordinates and subtract them. Cool, but what if you have 10,000 x coordinates? What do we do then? And I bet you could do it, but let's take a peek. So using 7 equal subintervals, find the length of each delta x on the interval from 4 to 9. You're like, yes, finally, back to numbers. Let's see how this works. Well, we, of course, have our xy axis, and we're looking from 4 to 9. And I'll just do, this is the most generic curve of all time. Like every professor that I've ever had draws a curve that looks something like this, so I might as well continue the trend. Okay, we're looking from 4 to 9, and we want to split that distance into 7 equal subintervals. Well, how do you do that? Okay, split it into sevenths, so there's 1, there's 2, there's 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Woo! There's 7 subintervals. Cool. What are the x coordinates of each of those? Maybe you're like, oh, is it 5, 6, 7, 8? Nope, that's not it. Drat. Well, how do we do this? Well, essentially what we're doing is we're saying take the distance from 4 to 9. What is the distance from 4 to 9? We subtract to find distance, that's 5. So this has a total distance of 5. And then we're going to split that distance of 5 into 7 equal parts. So couldn't we just do 5 and then divide it by 7? And this right here is going to be our delta x. If you wanted to go further and say, well, wait, what does that delta x actually mean? Well, you can give it two meanings. The first is that is the distance between any two x values. But you can go further and say that actually is the number that lets us figure out what all the x coordinates are. And I'm going to alternate above below because otherwise I'm going to run out of room. But to find each one, if we start at 4 and the length is 5/7, then this next number or x value has to be 4 and 5/7, doesn't it? And then you got to be decent at adding fractions here, but I have faith in you guys. If we add another 5/7, well, adding 2 7ths will bring us to 5, and then adding 3 more 7ths will bring us to 5 and 3 7ths. And then we continue on, right? So our next one, we add 5/7, so 4 will bring us to 6, plus 1 more is going to give us 6 and 1/7. Ooh, we haven't had fractions like this in a long time, have we? And then we add 5/7. Ooh, this keeps us under it. So this is going to keep us at 6 and something, 6 and 6/7. And then we add 5/7 again. What are you doing to us, Mr. Grant? We're adding fractions. Yes, we're adding fractions. So add 5 more 7ths. 1/7 will bring us to 7. That leaves 4 more 7ths. So we have 7 and 4/7. And now the moment of truth. We see if I've done everything correctly. I need to add 5/7 to that. So 3/7 I think will bring us to 8, and that leaves 2 more, so 8 and 2/7, and then add 1 more to that. I did do it right. That's going to give us 8 and 7/7, or 9. Cool. So we were able to split this, though, by just 2 easy tricks. This is the bonus. This is the important piece. How did we do it? There were 2 steps. We subtracted the endpoints, and then we divided by the number of subintervals. Now, just showing you this in terms of a more generic example, this is going to be very common. Eventually, you're going to get to classes where they just stop giving you numbers all the time and just say, oh, we'll just give you a generic example every time. And you're like, no, bring the numbers back. So I try my best to make sure that we have a concrete example and one that's a little bit more abstract. But here's what we're doing. We have an interval from A to B. We have our usual curvy curve. Okay? And the question is, we want to use n equal subintervals. Then find the length of each delta x. Well, if there are going to be n subintervals, the very first thing we need to do is we need to at least figure out how long the interval is. And that means we need to do b minus a. That's going to be, if you wanted to label it, the length of the interval, right? In the previous problem, the length of the interval was 5. Okay, it's the distance, total distance. And then once we have that total distance, we need to subdivide it into some number of subintervals. In this case, how many subintervals? Well, we're making it generic. We said n subintervals. So our second step to start to subdivide, or maybe I should put these 3 up here, to start to subdivide all these intervals down here, is we take the length of the interval, this was 5 last time, right? And we divide it by the number of subintervals. So maybe we do 5 divided by 7, 5 divided by 10, 5 divided by 4. This, once we do that, will tell us how far apart every 2 consecutive x values are. Now, with that generic example, we are going to define delta x, and you've seen the definition, we just did it. But it's one that is used everywhere for the next few weeks. So the length of one subinterval from n total subintervals is given by, and notice our b and a over here, it's given by b minus a, the length of the total interval divided by the number of subintervals you would like. Now, the last part of this, before we can really move into our concrete examples, is going back to the graph at the top. We're going to decide on an interpretation of the product f of x sub k times delta x. So I'm going to write that a little bit larger. We have f of x sub k times delta x. We need to determine what each of these factors mean, and then what happens, or what do you get when you multiply them together. And one of them we already talked about. We already know delta x. Going back up here, delta x is just the distance between any 2 x-intercepts. But in the context of this graph, couldn't we also call delta x the base of a rectangle? Right? Isn't that what each delta x is? It's the base of a rectangle. All right, well then, so that's not too bad. So maybe we can interpret this as the base of the rectangle. And of course, there's this cute little multiplication sign. But then we have f of x sub k. So let's break down each of these. Let's start with x sub k. X sub k is just a fancy way to say an x-intercept. Let's switch colors one last time. An x-intercept. Each of these are x sub k's. This is when k is 1, when k is 2, so on and so forth. Those are x values. But when we do f of an x value, f of an x value creates a y value. So for example, if I wanted to look at this point right here on my graph, it has to be on the function. This is the function f of x. This is f of x sub 1. All right, and you can see the rest, f of x sub 2, f of x sub 3, so on and so forth. So if we look at this guy right here and we draw up to it, what is that? Well, it's not the height of the first rectangle, right? The height of the first rectangle has that extra piece up at the top. But isn't this the height of the second rectangle? And f of x sub 2, that's the height of the third rectangle. And f of x sub 3 is the height of the fourth rectangle, the distance from the x-axis to the function. And so knowing all of that then, if we can say that f of x sub k is the height of a rectangle. Pretend that's spelled correctly. Now it's going to bug me. Rectangle, crushed it. And we're multiplying just a base times a height, then I believe this will give us the area of one rectangle. So what was the point of all of this? Well, the point of all of this was first to introduce different notations that we're going to see over the next few days, but second, to give us a really succinct, easy way to describe how to find the area of one rectangle. But how many rectangles are there up here? 1, 2, 3. It looks like there are 7 of them. And so if we wanted to find the total approximation for the area underneath this curve, I think we would have to add up all 7 of those rectangles. So here we go. This is the area of one rectangle. Here is the area of another rectangle. And of course, we have the dot, 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 the ellipses, it's kind of the floating ellipses, to show that there are some number of rectangles, right? This is going to be n number of rectangles. In our case above, this would probably be a 7 to show that we are adding up 7 rectangles to find the area under the curve. This idea where we have a sum of products, where we are adding up multiple different products, is known as a Riemann sum. A Riemann sum is defined as the sum of areas. Who is Riemann? Well, he was a wonderful German fellow. He was born in the early 1800s, something like 1826. Bernhard Riemann. The guy was a genius. Oh my gosh. He is considered one of, I could say top 5, but we're just going to go vague and say one of the most influential and famous mathematicians of all time. I mean, just absolutely insane how much of many different math fields he revolutionized. Geometry, calculus. He's the one that came up with the first rigorous definition of an integral, of a definite integral that we're going to move over to in the next couple of days. Honestly, I would tell you more about him, and I can give you a little history. We might as well start with that. But I can't tell you too many specific things because everything that he worked on, I don't understand. And so you guys will have to do some research into it, but I'll show you a couple things. Either way, some history. Born in around 1826, his dad was a pastor, and he was raised assuming that he would follow his father's footsteps and go into the church. At the age of 19, he goes to university. He is a theology major, looking again to stick with the church. However, he is also taking lecture classes from a gentleman named Carl Friedrich Gauss, another incredibly famous mathematician. There's all sorts of stories about him. Probably the most famous about Gauss is he's, pick an age 10, 12 or something, sitting in a classroom and he's misbehaving. The teacher says, I want you to add up all the numbers from 1 to 100. So 1 plus 2 plus 3 plus 4. Gauss goes, okay, thinks about it for about 15 seconds and says, okay, here's the answer. The teacher's like, how did you add those up so quickly? Well, he didn't. He came up with an algorithm, and it's a very famous algorithm these days. But either way, you can look that up. Gauss, famous guy. So he is Riemann's professor at his university. And he quickly realizes Riemann's potential and says, hey, I mean, the church stuff is cool, but let's do math because that's where all the really, really cool people go. And Riemann says, okay, I'm in. Except it was very cute. He asked his father for permission first, and his father said, yeah, okay, go for it. Well, it turns out that Riemann was like one of the most gifted mathematicians of all time. And to try to put that into perspective, in the late 50s, 1850s that is, so Riemann is like early 30s or so, and maybe at the most. He is at a very famous university in Germany, and he is put on a lecture rotation, and they're like, hey, you need to start lecturing about all these things you're discovering. Well, he wasn't even a professor there yet. They weren't even paying him. So Gauss arranged for at least him to get paid, and they tried to just fast track it and said, this guy's brilliant, can we just give him a professorship? That kind of fell through, but at least he made some money. And so the craziest part for me is that he is world renowned for so much math. I mean, just an insane amount. And he died at the age of 40. Yeah, he died in like 1866 or something like that from tuberculosis. He had fled religious persecution from the Prussians, went to Italy, caught TB, died. 40. But yet he was still so influential and just, oh my gosh. I mean, I have a couple of his Wikipedia articles up here. Did I get any of the dates right? I did. 2666 Gauss. I mean, his Wikipedia articles, pretty good. I mean, not super long. But then you go to arguably his most famous legacy, outside maybe integration and a million other things, and that's the Riemann Hypothesis. It is one of the Clay Mathematics Institute's Millennium Prize problems. We'll talk about it at the end of the year. 7 huge problems in math that have never been solved, and the Riemann hypothesis has still not been solved. And man, you can read about this, but look at this Wikipedia article. I mean, dang. It is a really famous thing that has far-reaching implications, and I understand like 1% of it. Maybe I should probably study up on this, but it all has to do with his Riemann zeta function. So it's a function named after him too, and he's proving things about that function. In fact, he's finding zeros like x-intercepts and proving what they are. So look into it. Fascinating guy. Sad that he died so early. Still gave the field of mathematics lots and lots and lots. So let's get back to it. Riemann sums. Okay. This Riemann sum up here began with f of x sub 1. But that's kind of weird because in this up above, we start with f of x sub 0. So they went from f of x sub 1 all the way up to, let's say, f of x sub 7. Awesome. How about, though, if they had started with f of x sub 0? Where would the Riemann sum have gone then? Well, hopefully you would say 6, because we need to add up 7 rectangles. And if you start at 0, count with me, 0 is 1, 2, 3, 4, 5, 6, 7. Yeah, it's kind of weird when you include 0. You have to realize that there are 6 numbers from 1 to 6, and then 0 makes the 7th number. So just keep that in mind. Let's go ahead and get to our approximation methods, specific names this time. There are 4 approximation methods that you're required to know for the AP exam. We're only going to cover 2 of them today because somebody went off on a tangent, pun intended, about Mr. Riemann, and I don't think we'll have enough time to do all 4. So we're just going to do 2, and then you'll get some practice on this. The first method is our right rectangular approximation method, nicely nicknamed RRAM. Okay. Now, how do we do the right rectangular approximation method? Well, never forget, mathematicians are extremely uncreative, so the name probably describes the exact method we're going to do. We are going to approximate a function's area using rectangles that are drawn from the right. So, we're going to look at a subinterval, and we're going to begin on the right endpoint. You use the height of the graph for the right endpoint as the height of your rectangle. Once you've done that, you draw over to the left side to complete your rectangle, and that's it. Okay. So what does this look like? Well, we are going to have a very cute little graph over here. It's going to be generic. We'll do an example with numbers in just a second. We are starting at A. We are ending at B. We have the curve. Looks something like this. And we want to approximate this curve. Now, the number of subintervals is going to change from problem to problem. I'll just pick a few on here. It doesn't have to be perfect. We're going to assume that they're even for today. Okay, so I just split that into 1, 2, 3, 4, 5 subintervals. Go us. And in order to do this, we need to take each subinterval. Here is my subinterval. I'm doing it in blue. This is the right rectangular approximation method. So I need to start on the right side of the subinterval, draw up to the graph, and there is my rectangle. I have a base, I have a height. Now, if you want to go further, and you can, you probably should, I would suggest you do it with dashed lines so that you can see the part of the rectangle that's just implied from what we drew. Because what I find is if people draw it solid like so, then they look at it and go, wait, did I start from the left? Did I start from the right? So I like those dashed lines. And I'm going to switch colors really quickly. We have our second subinterval, and it's going to look something like this. So we have our solid, this dictates the height, the right side of the interval, and then dotted lines on over, right? Very easy all the way through. And you can continue through to the end. I don't really want to, so I'm just going to go up here. Here would be my last one. Very exciting. Once we do each of those, we have to find their area, and then we sum up the area. Now, just as a heads up, if you want to write out the pattern when you're summing up the area, okay, we need to certainly figure out the base. The base is just going to be delta x of each of these, right? Nothing bad, lots of delta x's. Okay, so if I wanted the area approximation, it's going to be the base times, well, how do I find the height of the first rectangle? It's not going to be A, right? I'm not going to do f of A. F of A would be this point. That point has no relevance for a rectangle. It needs to be this point. And that point is 1 to the right of A. But not 1 to the right, it's delta x to the right of A. So if you wanted the notation here, my first height of my rectangle is found by using the x-coordinate A plus delta x. A plus delta x, that's this x value right here. Delta x larger than A. And when you substitute it into f, it finds the height. This is a base, this is a height. We are very excited. Notice that I never used A here. You're going to add up all of the areas of our rectangles, ending with what? Well, we need to end with delta x, a base, times what's the last height of my rectangle? Oh, that's over here. The last height of my rectangle is dictated by b, so it's times f of b. So you'll notice that we never used the left endpoint in our Riemann sum for a right rectangular approximation. I am going to write that too. So we, exclude the left endpoint in our Riemann sum. Now, it's important to realize that when you are finding a Riemann sum, and this is a very common question on the free response, I almost guarantee one part will ask you to approximate an area using a Riemann sum, you are required to show both a product, something times something, and a sum. So if it says use a Riemann sum to approximate, a Riemann sum is defined as a sum of products, and you must show both. If you do this math in your head and then just show the addition, you will not get full points. You need to show the bases and the heights. All right, let's actually do an example here. Example 1. Using the right rectangular approximation method, determine the approximate area for f of x equals sine of x on the given interval for n equals 4 subintervals. Okay, let's start with a graph. Sine of x, I think I'm only going to need the positive portion here. Let's give myself a little bit more room in case I need to write. That's good enough. Okay, and then we know we're starting at 0. We're ending at pi. And remember, sine of x looks, I think, something like this. It ends at 2 pi, doesn't it? So I think we probably just need the curvy part, hopefully drawn a little bit better. Yeah, good enough. Sounds good. And then we need 4 subintervals. Now, you could just split this into 4. I prefer a little bit more of a logical approach, which means we're going to find delta x first. How do we find delta x? Well, we take the length of the interval, pi minus 0. That's a length of pi, easy enough. And we divide it by 4, which tells us that our delta x is pi over 4, and that tells us how we can create all of our x values on our interval. We start at 0. We add pi over 4. So my next one is going to be pi over 4. Now, just a little trick of the trade, if you know there's going to be 4 subintervals, right? There's 2 subintervals. There's 4. You can pre-divide this out to get 4 even subintervals and then fill in the values later on. So now that we know pi over 4, 0 plus pi over 4 is pi over 4. Plus another pi over 4, that's 2 pi over 4, or pi over 2. And this is 3 pi over 4 and pi. Great. Now we draw our rectangles. Looking at this, we need to look at each of our subintervals very carefully, and I'm just showing them in red over here. And we need to think about where we start on the subinterval to draw our rectangle. First subinterval, this is a right rectangular approximation method, so I look at this interval and I start on the right, draw up until we hit the graph. I like to put a point, and then dashed lines for the rest so we can see how we created this. Then for my next one, just switching colors so we can keep it straight, like this, dashed line, and over here. The third one, draw up, and like so. And my last one is really weird. The last one, we have to, I've run out of colors, that's awkward. We have to start, I guess I'm going to use red. We have to start on the right side, but then if I draw up, wait, I'm already at the graph. So when you draw up and then go over, it's just a flat rectangle. You can think of it as a rectangle that has a base of pi over 4 and a height of 0 if you'd like. And that's what I'll actually show in the problem in just a second. I'm using a lot of colors on here, and some people say, well, could I do that on the AP test? I like colors. And the official policy of the AP exam for math is no. You cannot bring multiple different colors. They pick weird lines to draw in the sand. However, you can kind of get by because you are allowed to use a pencil, a blue pen, and or a black pen, which means technically you have 3 colors. You have gray or graphite from your pencil, a black, and a blue. So you do have 3 colors if you would like to bring those. So just think about that for the AP exam. You're like, I love colors. Cool, you can bring those 3. Can't bring anything else, no highlighters, nothing like that for the AP Calc 1, but I'm just giving you an idea. Okay, enough diatribing. Let's get this done. We need to find the area of each of these rectangles. Okay, so to find each of these areas, we're just going to sum them up. Shouldn't be too terrible. The first one, though, I'm going to write using our confusing notation up above, and then we're going to finish it off using notation that isn't too bad. So my area is going to be approximated by using a base. Well, my base for each of these is pi over 4. So that's pretty easy. Each of those is pi over 4. So pi over 4 is a base times, how do we find the height of the green rectangle? We use the right x coordinate. It's a right Riemann sum. So f of, and actually we know f is sine of x, isn't it? So can we just write this as sine of pi over 4 plus my next Riemann sum also has a base of pi over 4, shocking, and it's being multiplied by sine of which x coordinate created the height? Oh yeah, the right one, so sine of pi over 2. Plus, and then we again have pi over 4. We get the idea now, right? And we're multiplying by sine, nope, different color, sorry. We're multiplying by sine of 3 pi over 4. And there is one more, so hopefully you have a little bit of space on here. The last one is plus pi over 4 times sine of pi. Now, notice by doing this, we actually didn't need a graph. We knew where to start, and we knew what to add every time, and we knew not to use the first endpoint of 0, right? We have 4 products in here, 1, 2, 3, 4, okay? So that means 4 rectangles, 4 subintervals, if you will, and we could just write that out. So ultimately, by the end of the next couple of days, you should be able to do these Riemann sums without drawing a graph. However, when in doubt, draw a graph. It's not a bad thing. It just takes a little bit of time. All right, let's approximate this area. So my area is approximated by, actually, I don't want to write pi over 4 a million times. Isn't pi over 4 constant to all of these? Let's factor that out. So pi over 4 times sine of pi over 4 is root 2 over 2, right? Plus my next one, sine of pi over 2, I know that, that's 1. My next one, sine of 3 pi over 4, second quadrant, still positive. And then my last one, sine of pi, is 0, right? Rectangle with a height of 0, we saw that before too. And then we're here. So if you want to continue to clean this up, you can. At this point, I would probably plug all of this into a calculator. So why don't you guys go ahead, take about 20 seconds or so, put all that into your calculator, and let's see what you get. And we'll see if it makes sense for an approximation. Okay. I'm going to do the same thing. I'm just going to use Desmos, and we're going to close Mr. Riemann for a bit. There we go. So it was pi over 4. Don't forget, you can use Desmos as a calculator. There's a standalone Desmos calculator app, too, if you want to download that. And it's not the graphing calculator one, just the calculator one. I'm going to be smart here. There are 2 of these root 2 over 2s, which simplifies just root 2. And there we go. We get 3.79223 whatever. Very exciting. So we said that is the approximate area underneath the curve. Are we done? No, we do need to go over one other approximation method, and our other approximation method is very easy now that we've done the right. This is the left rectangular approximation method. The only difference is on the subinterval, you begin at the left end point. Generic stuff first, so stir fry, yeah. First, so we have this piece over here. We are going from A to B. The graph. and we need some subintervals. Same 5-ish subintervals, doesn't really matter. Let's look at these subintervals. I'll do each interval in blue just so we can see the 5 of them. My first subinterval, we need to start on the left side. This is the left rectangular approximation. So we draw up and then dash over. Next one, we draw up and dash over. And the third one, let's do back to yellow again. We draw up and then dash over. We get the idea, and we finish over here with B, but we don't draw it from B, right? The last subinterval you have to draw from the left side, so you go up and then over. So when we write the area approximation of this guy, okay, we know that each base, because we're doing base times height for each of these, is delta x, easy enough. Okay, so we know it's going to be the base times the height. Well, the height of my first rectangle is dictated by the first x value this time, so that's going to be f of a, right? And then we have our second one, which is this guy over here. So we have our delta x. We'll do one more of these. And then what is 1 bigger than f of a? Well, this is a plus delta x. So this will be f of a plus delta x. Plus, where do we end? Well, the very last x coordinate we need is the start of this interval, so this is going to be not b, but b minus delta x, one smaller. So we end up with our plus delta x times f of b minus delta x. So on a left Riemann sum, we exclude the right endpoint, and in this case, that is B. Okay, example. I told you we're moving faster, so let's get to it. Using the left rectangular approximation method, determine the approximate area for f of x equals 9 to the x power on the interval 0 to 2 for n equals 4 subintervals. Okay, we're going to continue to draw a graph, but if you're feeling more comfortable, you can start not drawing a graph. We are going from 0 to 2. 4 subintervals. Okay, I bet you can divide this into 4 subintervals without finding delta x, but for the sake of things, I'll do it. Delta x is going to be 2 minus 0. That's the length of the interval split into fourths. So 2 fourths, 1/2. Oh, I bet it's not shocking then. You add 1/2 to get 1/2, 1, 1.5, which I'll call 3/2, and 2. Cool. All right, then we actually need to figure out the y values, I think. So if we look at each of these, actually, let's have fun. Let's do this without the y values, right? Let's just call them f of something for the y values. I think we can agree that 9 to the x is exponential. It grows up like that. And we can at least start with 9 to the 0th. 9 to the 0th is 1. I'm pretty confident about that one. I'm just going to sketch in my graph. I know it's exponential, I know it's increasing, and the cool part about this is we don't even need to know the y values to start. So let's go ahead and start building our left rectangular approximation. First interval, we start on the left, go up, and over. And I'll do something like that. Great. How do we find the area of that rectangle? Well, of course, the base is 1/2. So my area over here, the base is 1/2. I'll use blue for each of those. And the height is dictated by 0 right here. And to find that 1, didn't we just do f of 0, where we just did 9 to the 0th? That's 1, but we'll keep it as f of 0 for now, just so we can see the pattern. Next up, we again have a base of 1/2. I'm going to draw this rectangle in purple. We go to the left side of the interval. It's a left rectangular, and draw over. And so the height here, I think we would call f of 1/2, whatever that is. So this is going to be f of 1/2. Then we do our third one. Draw to the left, up, right? Start on the left side of the interval might be a better way to think about it. And we do the same thing. It has a base of 1/2, and the height was created by using that 1. So this height right here is going to be f of 1. And we said 4 subintervals, so we certainly need one more. We'll do this last one in black. Looks like this. Okay, and that again has a base of 1/2, and the height, what is that height? The height's dictated by 3/2, so it's f of 3/2. Great, I should say approximately. Okay, well now we should probably find the value. Couple things again. The 1/2 is common to everything, so I'm certainly going to factor out the 1/2. In fact, many people factor out that common base the first time every time. That won't work, of course, if the bases are different sizes, which we'll see later on. And then we need to start evaluating. F of 0, 9 to the 0th, that's 1. F of 1/2, 9 to the 1/2 power is like the square root of 9, that's 3. F of 1, 9 to the 1st, that's 9. And last but not least, f of 3/2. Ooh, buddy. 9 to the 3/2. Remembering that 3/2 is really 9 to the 1/2 times 3 might help you. We know 9 to the 1/2 is the square root, and then we have a third power here. Square root of 9 is 3, and then 3 cubed is 27. So plus 27, we're looking pretty good. My approximate area, let's do a little math here. This is 30, and this is going to be 40. Half of 40 is 20. Nice. Now, looking at this graph, we can tell just by shading in these friendly little rectangles here that the area I found, the area of, it didn't change colors, but that's oh well, the area that I found right here is not the total area underneath the curve, right? If I wanted the total area, I would need to include these little pieces as well. So we would call, because the 20 is less than the total area, we'd say that the 20 is an under approximation. So the last part of today then is, how do we know if we're going to under or over approximate a graph? So think about that for a quick second. Think about what made us under approximate this graph, and who the heck knows on the sine function, maybe this is bigger than this, I'm not positive right now, right? But what makes something over or under approximate a graph? And let's assume that our graph in this case is positive. So I'm just going to sketch the first quadrant for each of this. And I need a little bit more space than that. Okay, so go ahead and pause me. Let's see what you get. Ready, set, go. All right. Well, hopefully you came up with the idea of increasing versus decreasing functions. So over approximation, actually I probably should have done this in two ways. Sorry, hopefully you didn't draw those graphs. Awkward. I'm going to go ahead and sketch two graphs in the first quadrant like so. There's one, and here is the other. These are both going to be positive functions. You can recreate this with negatives if you'd like, but it's commonly done with positives. And one of them is going to show a strictly increasing function, and the other is going to show a decreasing function. And I'll put these on here just so we can see the graph. And the question becomes, when are these over approximated? Well, I'm going to go ahead and split this into a couple subintervals, doesn't have to be too many, and then take a look at how I can over approximate. Right? I'm pretty sure if I found the area of these rectangles as I'm drawing them, we would absolutely get more area than is contained beneath the graph. What kind of rectangles are those? Those are right rectangular approximation methods. So for a positive increasing function, then a right rectangular approximation method will over approximate. However, if it's an decreasing function, and I did those same subintervals, right, something like this, to over approximate this one, take a look at this, right? Looks something like this. Okay. And so seeing that, that is certainly going to over approximate as well. And so if you have a positive decreasing function, then our left rectangular approximation method will over approximate. Now you're like, whoa, do you remember that? No, definitely not. What they're going to tell you is they're going to tell you if your function is increasing or decreasing. And they might say, and we'll do this for our under approximation, they might say, oh, you have a positive decreasing function. We're like, cool. And then they say, we want you to perform a right rectangular approximation method for this function, for our positive decreasing function. Will that over or under approximate your graph? So I literally sketched this exact graph, and they've told us that they want us to do a left rectangular approximation method. Okay, and nope, a right rectangular approximation method, getting near the end, sorry, I'm struggling here, and we try that. So we say, okay, right rectangular. I think that's over approximating. I think that's rather under approximating. There we go. Right, I was saved by my poor artistic skills over here. That's unfortunate. There we go. Cool. So we draw those in. We can see they're created by the right side of each subinterval. That certainly under approximates. So if they give you this information, draw the graph and see if it over or under approximates. Probably finish up this last one. So this is going to be an increasing function over here. And since we're in the under approximation category and we already used RRAM, then we should probably use an LRAM over here. This is a positive increasing function, of course. And so if we tackle this one, let's see, left rectangle should go here. There we go. That's looking pretty good. Yeah, I think we find the value, the area of those three rectangles, we will certainly under approximate. Nice. Okay, 2 quick practice problems, and we're finally done. This is a long video. I do apologize, but I think some of it needed to be said, and maybe some of it didn't. Awkward. Okay. Let f be a function that's twice differentiable for all real numbers. We can take the derivative twice, nice smooth curves, no pointy points. The table below gives values of f for selected points on that closed interval. Use a left Riemann sum with subintervals indicated by the data to approximate the integral below. Show the work that leads to the answer. Okay. Now, looking at this, it seems a little confusing because we don't have a visual. I'm going to show you a visual and then show you how we can do it without the visual. So, visual-wise, there are some positives and negatives here to throw things off. So I'm going to go ahead and do something like this. Okay, and then we have a few x values. We have 2, 3, 5, 8, 13. Fibonacci, exciting. So 2, 3, 5, 8, and 13. How many subintervals do you see? I see 1, 2, 3, 4 subintervals, and they are not equal. So we don't need our delta x here. We just need to approximate this graph. Now to approximate the graph, let's see some of those y values. We have a y value of 1, a y value of 3, 4, and 6. So maybe I should have gone even a little bit further. So we have 1, 3, 4, 6, 1, 3, 4, 6. Doesn't have to be perfect. And we also have one with negative 2. Okay, so graphing these, we have the point 2, 1, 3, 4, 5, negative 2, 8, 3, and 13, 6. All right, left Riemann sum. First subinterval. First subinterval, left Riemann sum. We draw up to the function and then over. Notice I didn't connect these dots. You can if you want, but I think then you fall into the habit or the pattern of extrapolating what you think the graph should look like. You're like, I think it looks like that. And I'm like, you're wrong. I think it actually looks like this. I mean, who the heck actually knows? We just know those 5 points, so don't overstep your assumption. Okay, so there's the first one. And if I'm approximating the area, okay, then let's find the area of that first one. The base is 1, right? That's subtracting those two right there. And the height, and actually maybe I should write it like that. The base is found by doing 3 minus 2, and the height is 1. Great. There's my first one. Then we need to add on the second one. So second rectangle, left Riemann, draw up, and then over. Okay, this one has a base of, I should be using colors here, 5 minus 3, and then a height of this y value here, which happens to be this guy up here, that is 4. I should again continue to probably use colors here. That is 4. Great. And so this one was 1. Okay. Then we have our third one over here. The third one I'll do in green. Nope, I already did green. That's awkward. We'll use purple. So here's my interval. We use the left to graph this. So the left is over here. There's a point that's negative, but it still works. Okay, and then we need to find our area. But wait, the area is below the x-axis, so don't forget that. Negative, the base is 8 minus 5, and the height, of course, is negative 2. And actually, using this pattern, I bet we could even do the last one, couldn't we? There's one more rectangle clearly, but let's not even look at the graph. The last one, which we'll do in blue and then check on the graph, is going to be, We know it's above the x-axis. We're positive here. The base is nothing too bad either. The base is going to be, what have we done for the base for the other times? We've done subtracted, then subtracted, then subtracted. I think we need to subtract 13 minus 8, yeah? So 13 minus 8 is going to be my base, and just double checking over here. 13 minus 8 is the base, right? That's 5. Very exciting. And then how do we find the height? Well, on each of these, right, for the first one in black, we subtracted 3 minus 2, and then we picked this guy. And then in yellow, we did 5 minus 3 and then picked that guy. Purple, 8 minus 5, picked that one. And then in blue, 13 minus 8, we've got to pick this one. Why out of the interval are we picking the one on the left as opposed to the one on the right? This is a left Riemann sum. We always pick the height, right? These are heights, aren't they? On the left side of each interval. And so by keeping that pattern, you can actually do this without drawing a graph. Also note that we did not use the last endpoint here because with left Riemann sums, we exclude the final right endpoint. Okay, cleaning this up then, the integral from 2 to 13, so measuring the area beneath the graph, is approximated by, well, 3 minus 2 is 1, 1 times 1 is 1, right? And then this next one, 2 times 4 is 8. I don't know why I put a negative here. Oh, no, I'm not going to put a negative there. We already made it negative by putting it out front. If you wanted, you could do something like that. However you do it, though, the area better end up being negative. So 8 minus 5 is 3. 3 times 2 is 6. So we'll call it an area of negative 6. That's below the x-axis. And last but not least, 5 times 3 is 15. So I think finishing this out, 15 and 8 is 23. 24. 24 minus 6 seems like 18. Whew! Okay, last but not least. Let f of t be the function that's twice differentiable. This is supposed to say t then because it's f of t. Whoops, I will fix that hopefully by the time you get your handouts. Use a right Riemann sum with 4 subintervals indicated by the data in the table to approximate the integral below. Well, there is no integral below, so that's also awkward, but then we need to state if our approximation is over or an underestimate. So let's start with an integral. The integral that we're approximating here is going to be the area under the curve from 0 to 12 of f of t dt. Makes sense because we're going from 0 to 12. I'm going to look at the subintervals first and see if they're even. The first x coordinates I'm going to look between, think 0 to 3 up here if you want, is a distance of 3. The next one is a distance of 2, then 3, and then 4. So not even subintervals. However, I can start to approximate my area because I know all of the bases. My first base is 3. Now again, I'll try to do colors here. And we'll do a plus, and I think this will be enough room. All right, my next one, the base from 3 to 5, we saw that earlier, is going to be 2. That's the base again. And then my third base from 8 to 5 is going to be 3. And then my last base from 8 to 12 is going to be 4. So we have all those bases. Then we need to pick the height. The height is the y-coordinate of our data. So we look back to our first subinterval and say, well, wait, is the height 0 or is the height 3? And we know this because it's a right Riemann sum. We use the height on the right, so it becomes 3 times 5. And then our next one, 2 times 10. The next one, 3 times 20. And last but not least, 4 times 24. Okay. You might want to use your calculator here. We can clean this up. We end up with 15 plus 20 plus 60 plus 16, 8, 96. Cool. And then finishing this off, we have 80 right here. Let's remember that result. This is going to be 95. So we have 95 and 96. And 95 and 96 is going to be 191. I think that seems right. And let me know if I did it wrong. I'm sure you will. You guys are great at commenting. Great. We approximated a value of 191 using a right Riemann sum. But is this an over or an under approximation? Oh, well, look what they've told us. Our function is increasing for all values, and all these values are positive right here. So let's draw a quick increasing graph, like so. And then we did a right Riemann sum. So we're just going to split this into a couple subintervals to get a picture. Look at my interval right Riemann sum. Oh, look at that. I think we have overestimated my graph. because, based on the picture. So how do we write our conclusion then? We would say something like the integral from 0 to 12 f of t dt approximately 191 is an overestimate because we used a right Riemann sum approximation on a positive increasing function. Right, just explaining what we drew up here. Finally, that is it for today. Next class is going to go much faster now that we all have the background. All we're going to do next class is learn the last two methods and do some practice. So thanks for sticking it out, and I am excited to have you back next class for our last two approximation methods.